Hello everyone, this is Team Spinning Falcons for the data structures project. Our data structure is the Octree, which is basically a 3D space partitioning structure. We've given the intro last time, and hopefully you know better from the presentation of my two colleagues over here. So I'm not going to dive too much into what an Octree actually is, so I'll just go on to show you. So in the last video, what we had was we had an Octree of depth level 1. Well, I'm glad to announce that we've changed that, and now we can have an octree of multiple depth levels. And with each depth level, the the original object gets approximated into various degrees. So, for example, we have constructed a couple of models from our original Bugatti model, and this is the octree. This is the model that is created when the octree is limited to a depth level of 4, right? And as we go along, this is the model that is created when the octree is limited to a depth level of 6. So we can see that it's a bit more detailed, but it's still sparse as of now. And moving on, this is the octree that is created at the depth level of 8. And you'll see that it pretty much resembles the original car except for the faces, but since we are working on a point cloud on only on the vertex side, so this is as close to a detail as we can get. And finally, this is the octree at depth level 10, I guess. And you can see that it's the difference between 8 and 10 is much smaller compared to the difference between, let's say, uh, 6 and 8. And this is the octree. Finally, this is the Bugatti that is constructed from an octree which is limited to a depth level of 15. So between 10 and 15, we can say for sure that the difference is quite minimal, and that is because as we increase the depth levels, we are able to accommodate more nodes in our octree. And that basically means that instead of approximating the model, we end up storing all the points of the original model, and that in certain ways defeats the purpose of an octree. So what we generally have to do with an octree is to find a good balance between, let's say, storage and visual fidelity. So coming to the point of storage, so this is just the code that we ran earlier, and for different depth levels, uh, we created an octree and we calculated number of vertices and the number of cubes uh, that the octree generated versus what the original number of vertices were. So for this run, we had set a depth level of 4, and the original vertices is around 3/4 of a million, and the number of vertices is 58,000, which is much less than what it is. And I think that amounts to almost 14 times decrease in points. But we all saw that the visual fidelity was not that good, but it was still quite pretty good. And here we have an octree of depth level 12, and the original number of vertices is still the same, 744,000, and the number of vertices this time that we were able to store in the octree is 670. And the cubes are much larger because for each vertex that we store, we have to create multiple cubes. And we can see that there needs to be a balance between these two cases, where the number of original the where we get compression from the original number of vertices, but the visual fidelity more or less remains the same depending on the purpose that we are using our octree for. So now I'm going to show you the part where we included the faces of the octree. So this is going to be another Blender run, and we have created these two octrees with depth levels of 8 and 12, right? So this is the face that we created. We extracted faces from our octree, and we could only get only a limited amount of data, and especially with the limitation of the depth level, we can do only so much. So this is the front grille of the Bugatti, and this is created at depth level 8. You can see that there are some lines here and there missing in the model. And if we move on to the other model, this is much more cleaner looking. This is much more sharper. The details are much better preserved compared to the one on the right. So what we've done here is basically we've again adjusted simply the depth levels, and that's basically it. And one more thing that an Octree does is for in-game engines that it's in its real world usage, that once you zoom in on a region, you can basically cull that region. You can basically only use that part of the Octree to create your render. So what we did here in that case as a demonstration is, instead of the entire Bugatti, we told our Octree to store only within a certain limits of X, Y, and Z, and for that we can go much higher on the visual fidelity. So for example, if you are in real world, if you are viewing only a part of a model, we can go much higher on the visual fidelity in that case too. So that's basically it. And yeah, that's basically it. So when we are this is a form of culling basically. So when we cull objects, we are able to remove the objects that we do not want, that we do not need in the, since it's not in the camera, and for the rest that we have left, we can go much higher on the visual fidelity. So what that and one more advantage of using this culling technique is that basically it limits the memory usage, because at first, while you had to render the whole card, now you only have to render a part of it, and you, even though you do go much deeper into the quality, it's still much lesser than the whole rendering the whole car. So this is one advantage of Octrays, is that you can use culling techniques such as this and other techniques such as frustum culling to efficiently limit your rendering to only where you need it and to a degree of quality that you want. So that's basically it from our project, and thank you.